Hello and welcome to Nikolay's genetics lessons, and today's problem I got from one of my subscribers, and here's the problem. A healthy 23 years old Maria comes to physician for genetic counseling with her husband John. She would like to become pregnant in the near future, but have concerns that their offspring may develop cystic fibrosis. Her sister Helen has cystic fibrosis, an autosomal recessive genetic disorder with incidence of the approximately 1 in 9,000 in this particular population. Nothing is known about the history of this genetic disorder in the Jones family. And here we have to answer these three questions. In order to solve this problem, we have to use hardy-weinberg formula, which gives us frequency of the three genotypes in a population, which is p squared plus 2pq plus q squared, and all of this combined equals to 1. And p squared here stands for the homozygous dominant genotype, so capital A, 2pq stands for the heterozygous genotype, and q squared stands for the homozygous recessive genotype. And according to our problem, we know that frequency of this genetic disorder is 1 in 9,000 people. So we can say that 1 out of 9,000 people would be affected with this genetic disorder. So I would put in red parentheses to specify that this part of the formula stands for the frequency of the people with this genetic disorder, and that means that the rest, which would be homozygous dominant and heterozygous, would show normal phenotype. So right now we are answering the first question: what is the probability of John being a carrier? So nothing is known of this genetic disorder occurrence in his family, so we just suggest that he is just average person from this population, and we describe this population in connection to this genetic disorder with this formula. And according to this formula, frequency of the Q allele, and Q here stands for the recessive allele, so Q stands for the recessive allele A, would be as follows. So we have to take a square root of 1 over 9,000, because this frequency is small a times small a. So if we want to find small a or q, we just have to take a square root of this number. And the answer as a decimal number is going to be 0.01. In this population, for this particular locus, we have only two alleles: dominant allele A and recessive allele A. So if we know the frequency of the recessive allele A, or according to hardy-weinberg formula, P plus Q should equal to 1. So two alleles, dominant allele A and recessive allele A. And 1 in our formula equals to 100%. So we can do calculations on the scale between 0 and 1, or 0 and 100%. And if we do our calculation on this scale, 1 equals to 100% here. So all the alleles in this population combined would equal to 100%. All three genotypes that can be made by these two alleles also would equal to 100%. Only three genotypes are possible as combination of these two alleles. And we have found that frequency of the recessive allele is 0.01, and frequency of the dominant allele is going to be 0.99. Now we can calculate probability of the John to belong to this genotype, which stands for the heterozygous frequency of the heterozygous genotype. 2pq would equal to 2 times p, which is 0.99, and times q, which is 0.01. And the answer is going to be 0.02. This is the answer for the first question. This is probability for John of being a carrier, so belonging to this genotype. Now let's answer the second question. What is the probability of the couple having an affected child? According to our problem, we know that Maria has a sister, Helen, that has cystic fibrosis. This is going to affect our calculations. So take a look. First of all, let's write down a pedigree of this family. So here's a family of the Maria. So father, mother, Maria, and her sister Helen. And we know that Helen is affected. So let's show it that she is affected. This is autosomal recessive genetic disorder. That means that genotype of her sister is small a, small a. And that means that genotype of her mother and father have to be heterozygous. They are phenotypically normal, but they have affected daughter. That means that their daughter have to inherit recessive allele from each of the parents. Now he is a Maria and he is a John. He is a John. We have found that his probability of being heterozygous would be 0.02. Why we are interested in probability of him being heterozygous? Because only in this case they may have affected child. Now we have to find the probability of his wife, Maria, of being also heterozygous. And only in this case they may have an affected child who is going to be also small a, small a. So what is the probability of the Maria being a carrier? Take a look. We know genotype of the parents, which is heterozygous. They obligate heterozygous. And when we build a Punnett square, take a look what we are going to see in their progeny. Capital A here, capital A small a here, capital A small a here, and small a here. We know for sure that Maria doesn't belong to this genotype like her sister, otherwise she would be affected. So we can exclude this variant. So we can say that she is healthy and she belongs to one of these genotypes. So according to this Punnett square, her probability of being a carrier is 2 out of 3. So we can put this number here. So 2 out of 3. And our final calculations are going to be as follows. So probability of Maria of being carrier, 2/3 or 0.66 as a decimal number, times probability of the John being carrier, which is 0.02, 0.02. And if both Maria and John would be carriers, it's not necessary that they would have affected child. Take a look. If they both would be carriers, the probability of getting affected child would be 1/4, or decimal number is going to be 0.25. So we multiply all these three independent probabilities and we are going to get 0.003, and this would give us a probability for the child to be affected and belong to this genotype. If you need an answer as percent, we have to multiply our answer by 100 and we are going to get, so we move this decimal point 2 places to the right, we are going to get an answer 0.3% would be a probability for the child to be affected with cystic fibrosis. And as you remember, the last question was, what is the probability for the child to be normal? So our calculations are pretty easy. 100% minus 0.3%, and we are going to get 99.7% is the probability that the child is going to be phenotypically normal. And this is all for today. Subscribe and see you in the next video. Goodbye.